Hello, this is Paul Randal, and this is the demo that accompanies the Weights and Queues module. What I'm going to do in this demo is I'm going to set up a couple of different scenarios and show you using the weight stats DMVs to have a look and see what's going on the system. So the first scenario I'm going to set up, I've got a script here, and I'll just show you quickly what it's going to go and do. It's going to create a database, and it's not going to do anything special with the data files and the log files. They're both going to be put in the same place on my C drive. It's got a table with a bunch of different column types. Noticeably, there's a GUID, and the GUID is going to be the primary key that I'm going to create from my clustered index. So I'm going to set all this stuff up, and I'm going to clear the weight stats DMV so I get a good look at what's happening just from this demo. So I'm going to go ahead and start that demo. So I've created my scenario, and the other thing that I'm doing is now that I've created my scenario, I've got 4 threads that are started up, 4 connections started up to the server. They're each going to try and insert 4 million rows into that table with a batch size of 10 rows in each transaction. So let's have a look and see what's going on in terms of weight stats. So this is some code that's going to look at all the weight stats that there are for the system and kind of group them together and tell me what is the highest percentage. It's based on some code that fellow MVP Glenn Berry wrote a while ago, and I've made a few modifications to it. So let's go ahead and run this. And what it's showing us is the prevalent weight types. So it's going to list everything that has more than a couple of percent of the total number of weights. The prevalent weight types, the total time that this particular weight type has been weighted for in seconds, and then the resource weight, the signal weight, the number of weights that have actually occurred for this. This is the percentage of all weights that there have been on the system so far, and then it's got the average wait time, the average resource weight, and the average signal weight. So remember the definitions of resource weight and signal weight. The weight time total is a combination of resource weight and signal weight. So the resource weight is the amount of time that the thread is waiting for the resource to become available. It's then put on the runnable queue, and the amount of time it waits on the runnable queue before it actually gets the CPU and is running is the signal weight. So what we're seeing here is basically the write log wait is the one that's taking the most time. Now the write log wait is essentially threads waiting for log buffers to be written out to disk by the log manager. So we could go and dig in a little bit more. So there's another script that I could show you, and this is looking at waiting tasks. Now this is another piece of code. It's based on code by a guy called Joseph Sack, who actually runs the SQL MCM program. And what this one does is it drills in a little bit deeper to the weights to look and see which tasks are actually waiting for something. And what this code does is it cross-applies with the various sys.dmexec DMVs to be able to pull out more information about what it is actually waiting. So we go ahead and run this. We can see basically we've got our 4 separate connections, and each of them are waiting for write log. If we go across, what we can see the actual text of what's running, and we can see an XML query plan. So if we pull up the XML query plan by clicking on it, there's the query that's actually being run in each of my separate connections, basically just doing a big insert into the clustered index. Now, if this was on a more complex system, obviously this is a completely contrived example. If this was on a more complex system, you'd be able to use this piece of code to actually dig in and figure out which connections are experiencing the most weights and see what queries are actually generating the most weights. So I'm seeing a lot of write log, so let's just update that again. So now we're definitely seeing write log as the overriding cause of the weight. So let's have a look at perfmon, and we'll go in perfmon, and let's get rid of processor time. Let's have a look at our transaction log. So we go down to the databases perfmon object, and let's look at log growths, for instance, for my database weight stats demo. Let's add that in. I don't want the total, so let's get rid of that. And I also want to look at physical disk and see what the wait times are for operations on physical disk. So I'm looking at, not going to look at queue length, because SQL Server can drive queue length higher than single digits, that's well known. What I want to look at though is average seconds per read and average seconds per write. So I'm going to look not at total, I want to look at C:, and D:. So add those in there, then hit OK. So what I'm seeing, if we go down to log growth, and let's make the properties of that scale 1. I'm seeing I've done an awful lot of log growth since I created that database. And then as far as C: is concerned, so the average disk seconds per read, let's highlight that in black. But the one I'm interested in is average disk seconds per write. So what we can see there is we've got quite high times that we're having to wait for some of these IOs to complete. Now, write log waits can usually indicate that there's an issue with the IO subsystem. Now, it doesn't always indicate that. You sometimes, if you've got a system with an awful lot of concurrent connections and they're doing lots of operations that are going to require logging, it could be that the spin lock that's required as part of flushing out the log buffers is what's actually causing some of the wait time. So to be able to make absolutely sure that it's the IO subsystem that's causing problems, you have to look at the virtual file stats, DMV, to look at how long the real IO waits are for the log drive. But in this case, I know that I don't have a really heavily loaded system in terms of concurrent operations, so I'm thinking that write log is a problem because I have the log and the data file on the same drive in my laptop. So what I'm going to do is I'm going to stop this particular test. Let's kill all these threads. And then I'm going to start up a second demo. And what the second demo is going to do, I'm going to leave these weights here. So the second demo, if I show you this script, is going to change the definition of the database a little bit. It's going to drop the old database. It's going to change the database such that on the C: drive I have my data file, and then on D:, which is a separate drive in my laptop, I have my log file. Now, instead of creating it with the defaults, I'm creating the log to be 512 megabytes in size, and I'm creating a large file growth, so we shouldn't see so many file growths. Now, I'm keeping the table schema exactly the same. Now, the other thing that I'm going to do is, let's keep this going. The other thing I'm going to do now, instead of having 4 threads, each one of those threads having a batch size of 10 trying to insert into the table, I'm now going to have 2 threads, each of them having a batch size of 100. So that means I'm going to be doing less log buffer flushes, because the log buffer can grow any size up to 60K. As soon as a transaction commits, then the log buffer is ended and has to be flushed out to disk. If I have larger transactions, then I shouldn't be committing transactions quite so often, and I shouldn't have quite so much in terms of write log waits. Now, I'm also, because I've split out the data file and the log file, I shouldn't have quite so much in terms of write log waits either. So now let's fire up wait stats demo 2, which is just the same code that I had before, but I want to run it in a separate window so I can compare against the wait stats from the first part of the demo. So what I've done again is I've changed the database setup, and I've changed the way that I'm running my inserts. Now, just having a little bit more of a look here, you notice that I'm skipping a whole bunch of waits. Now, these waits can happen all the time on the system, but they're not things that you actually have to be concerned about, usually, in terms of performance tuning. So let's go ahead and run this again. And we'll compare it with the waits from the previous demo. So let's see, look at what we're doing. So now we have a bit less of write log. So before, write log was 75% of the waits, and now we're seeing that write log is only 24% of the waits. And I've got a much better, much clearer view of what's going on inside my system, because write log was basically meaning that everything was all the other waits were essentially being masked by the fact that there were so many write log waits. Now, there were some buffer pool flushes, which means I was waiting for data file writes as well. But over here, when I've changed my database physical schema, you can see that I've got a lot less contention for the log. I'm now seeing some more buffer pool flush weights, but I'm also seeing a bunch of weights that's telling me that I've got I/O subsystem contention problems on my data file now as well. So I've managed to split things apart. I've changed my setup a little bit, and I'm seeing some different weights. So let's just refresh this. And now we're seeing the changes actually very much more pronounced now, that the data file has now got the majority of the weights, and even though the write log weights there's a lot of them, the fact that there's a lot of them and they're very small means they're not something that I particularly have to worry about. Now, just because I'm seeing all these different weights, again, it doesn't mean that they're necessarily things that I have to worry about. Now let's have a look at our perfmon. The trick, of course, again, is knowing what it is that's actually relevant to look at. Now, you can see that the average disk seconds per write for C:, is a lot lower than it was before. Before it was up around the mid-20s, and that's in terms of milliseconds, with occasional spikes. And now it's down here. Okay? So from, say, 10, 11, 12 milliseconds, is that something that I would consider reasonable? Yes, probably. And we see we have an awful lot less log growths because I've changed the dynamics, essentially, of what's going on with the transaction log. So by looking at the weight stats, doing a little bit of investigation, I've used the weights from demo 1 to figure out which queues to look at. Remember the whole weights and queues methodology. And I've made some changes based on what I've seen in terms of the queues, and that's enabled me to actually get better performance out of my system. Now again, totally contrived example, but the kind of way of working through this is what you would do on a real system. Now, one more thing I want to show you is if I fire up a third demo, and what this demo is going to do is it's actually going to add in some loops that are basically trying to do select count star. So what we're going to see, because we've got inserts happening as well, is we're going to start to see some blocking. So I do this. I run a third set of these weight stats. And what we should see, oh, it finished already. No, it didn't. We should see some locking. My first set of inserts actually completed. So let me run my first set of inserts again, because I'm not going to get any blocking if I don't have any inserts going. So there's my inserts happening again. Now, if I have a look here, is this still running? Okay. Start up my inserts again. This is the problem whenever you're trying to do any kind of performance demos. No, it still didn't run. And there we got a lock block, and there we got a lock block as well. So we managed to stop things in the middle of the select running as well, and we saw that now by adding in a select workload, then we suddenly started to see an awful lot of blocking. Now again, we'd be able to look using the waiting tasks DMV to figure out which one of these connections is seeing the various blocking happening, and maybe figure out, well, there could be a missing non-clustered index, for instance, that's causing the select to go and run over the clustered indexes, which is exactly what's happening in this case. By putting on a non-clustered index, we might be able to cause those selects to use the non-clustered index rather than the clustered index, and then we wouldn't have the blocking problems. So again, using the weight stats to figure out what queue, in other words, what resource the problem is with, and be able to take some corrective action based on that particular resource. One other thing we notice down here is we've got a CX packet weight. CX packet weights are basically, inside the query processor, multiple workers doing the operation that we've asked to do in parallel. And CX packet weight indicates that some threads are completing faster than others, and so the CX packet wait is these other threads waiting for another part of the parallel query to complete. I hope you read through or listened to the weights and queues lecture that I gave, because that has a bunch more information about resource weights, signal weights, what those are, and the various queues that there are inside the scheduling system of SQL Server, and how these various weights play into that. There's also going to be a link in there to a set of resources, including a very, very good white paper called Performance Tuning with Weights and Queues that you can use to figure out what all the different weight types are. So hopefully this demo has given you a good indication of how you can figure out what the weights are and some of the things you can go and change. Again, very contrived example, but it does show you the kind of concepts that I wanted to give. Thank you.